What makes the wind blow? Starting with a sea breeze model, I'm going to try and explain the global circulation and also talk about Coriolis, which is caused by the Earth's rotation, and fronts in the mid-latitudes, which help distribute heat around the Earth. So let's have a go. Solve these equations and you'll understand what makes the wind blow. So it's to do with momentum, gravity holding the atmosphere down, conservation of mass, and heat driving everything. So let's try and explain it in more intuitive ways. So a previous lecture I looked at the heat budget of Earth, which is heat coming in from the sun and being radiated out and exchanged with the greenhouse gases. But it's not even, the heat coming in, it's unevenly distributed, so the redistribution of heat is what drives our weather. And a sea breeze blowing from the sea, in the same way that a northerly blows from the north, is caused by uneven heating in a more local situation. So to start off with, we have air masses over the land and the sea at a similar temperature. Then during the day the land heats up, so that air column expands and it starts spilling out towards the ocean. So that moves mass from over the land to over the ocean, which means there's less weight on the surface below, so you get a low pressure developing over the land and a high pressure over the ocean, which pushes in the sea breeze. So the same kind of thing happens on a planetary scale, and in that high pressure area you have sinking air, and in that low pressure area you have rising air. And sometimes you can notice that on the coast as well. So out to sea there can be clouds, inland you can have clouds, but in between where you've got that high pressure area you've got a blue space. So look out for that. You can often see it on the satellite as well. So if we were to go sailing towards the sunrise with the wind on our back, let's just say the wind is blowing directly towards the sun. Now the wind doesn't know that the Earth is rotating underneath it. So Coriolis is just inertia, Newton's first law saying that things will keep doing what they're doing unless there's a force acting on them. So the wind is going to try to keep blowing towards the sun. So as the sun rises up, it's going to try to blow up to that point there. But Coriolis is very weak compared to gravity, so the vertical component doesn't matter. It's only the movement of the sun to the side, which is left in the southern hemisphere, which makes a difference. So Coriolis is going the same way. So in the southern hemisphere the sun rises in the east, it swings around to the north during the middle of the day and sets in the west, and that is always going to the left. In the northern hemisphere it's the opposite way around, and if we were over the equator the sun would be rising more straight up, so that horizontal component is very small, so the Coriolis force is weak in the tropics. In Antarctica during the summer the sun stays up all day, and these crystal balls, a meteorologist's favourite tool, simply focus sunlight onto those cardboard cutouts, and they burn a mark when the sun's out, so it lets you track how many hours a day of sunshine you had that day. So during the daytime the sun moves around this way and shines on the daytime bulb, and during the night it moves around this way and illuminates this one. Now this is a track of tropical cyclones, is what we call them down here, typhoons or hurricanes if you're in North America. And you can see that there's a gap here around the equator, so they need Coriolis force to turn and organise them into those, rotating gigantic tropical cyclone storms. So that's one thing to notice. They need to be a little bit away from the equator. Another thing is that they start off having a drift like being blown by easterly winds, and then as they get lower down in the mid-latitudes they become more westerly, and that happens in the northern hemisphere as well. And also notice that it's really green in this central part of Africa, and it's desert on either side. So with the sea breeze going into the hottest part of the earth, you get all that moisture being brought in, and this lush tropical rainforest through here. But as it goes up and then comes out in the upper levels and sinks down again, you have these deserts. So let's have a look at that. So you have to look really close, but here is the monsoon trough, and if you look at the tiny little clouds, they're flowing in towards it on both the north and south side of it. Over here the trades have got an easterly component, so it wants to flow up towards the equator, but it's being turned to the left by Coriolis. And you can also see over here that they've got a southeasterly movement on those clouds. And now we can look at the upper levels, and you can see on the monsoon trough that the upper air is flowing outwards on both sides of it, and over here you can see it's flowing outwards as well on both the south side over the top end of Australia and over here on the north side. Now these average movements of air cause these easterlies at the equator, and because you've got high pressure here sinking down with the return of the sea breeze, you've got these westerlies in the mid-latitudes. This is actually ocean currents, so over time they push the water along, and then the water turns to the left and you get this Humboldt flow up the coast bringing nutrients to the Galapagos Islands, in the same way that this cold current comes down from Labrador, and you've got the Grand Banks there bringing nutrients to what used to be the richest fishing ground several hundred years ago until they fished it out a few decades ago. And you've got the warm currents being turned around and brought to heat Europe. So let's get this show back on the road. So recapping, this is what we call the Hadley circulation. It's a planetary sea breeze that brings trade winds to converge in on this monsoon trough. And in the upper levels, we have it coming back the other way and these dry zones in between. So storms where it's rising, desert where it slowly sinks over days and a week or so. It's a slow descent of the air here, but obviously storms are quicker, they're over a few hours. And yeah, monsoon trough, trade winds, subtropical arid belt either side, and down here the westerlies. And because the Earth is too big to just have one Ferrel cell, you've got a few more similar circulations which aren't as well defined. They're called Ferrel cells. So this is a satellite picture of the fires last year in Australia and a front passing through. So on this side of the front we've got a warmer tropical air mass, and down here in the bottom left we've got a cooler air mass coming from Antarctica, and in between them a planetary sea breeze would want to blow the air that's expanded upwards. In the upper levels it would want to flow out into the cold air, but it is turned by Coriolis to the left, so the upper levels has airflow flowing down this trough line, and because of reasons I won't explain in this video, that air mass stretches out because it's going towards the poles, and that means there's less air sitting on top of the air underneath, so it becomes a low pressure trough. And in the lower levels, air would want to fill into this trough, but again, Coriolis turns it, so it won't go directly into the trough, but it will get turned to the left. That helps keep the low pressure existing, so it doesn't just fill in. And also, because it's being turned, it's bringing colder air in on this side, coming from the poles, and warmer air on this side coming from the tropics. So that helps maintain the temperature difference across the front. So here we have the descending air coming back from the monsoon trough a long way away, subsiding, and it's warm because sinking air warms, the same way rising air cools. And underneath we've got trade winds, which have come from the south. They're blowing over the barrier reef, what's left of it, and cold air under warm air means it's quite stable. So in that situation you don't have any vertical mixing. So inversions, where you have warm air over the top of cool air, mean there's very little mixing and that the winds can be completely different. And they often are, as we saw when we were looking at the satellite picture before. So another way you can have an inversion is when you have cold air over land during the night, and that's typically when you have the winds drop out. When you have thermals during the day, it mixes that upper wind in again, but during the night you just have local winds like flows sinking down out of valleys. So here's an example. In northern Australia there's an island which has this storm form over it quite regularly in the summer, because sea breeze comes in from all sides, converges in the middle. If the conditions are right, you get a storm, and you can see it kind of flowing out with this anvil again. So that is a nice little analogy for a global circulation. Like, you could pretend that you've got trade winds coming in, a monsoon trough in the middle, and then outflow at the top. That happens on all kinds of scales with meteorology. And lastly, there's a similar situation in New Zealand. This is north of Queenstown, near the centre of the island, where basically you have wind on my back, so I can't fly from where I am. And there's also wind coming in from the other side of the island, and it's converging in the middle to have this beautiful convergence line. That would be a great place to be flying.